Hi, my name is Parker Kelly, and this is my video going over the Design Assignment 4 report. My group members was Hannah, Edward, Pedro, and Ashley. So for this project, we were tasked with optimizing the maximum transverse tip displacement of a piezoelectric that is attached to a polymer. So in the problem definition, we were given how much voltage will be put through, and as well as how much temperature will be put through the piezoelectric and polymer. And then the material information. So we are given the thickness, width, and length of our piezoelectric, as well as its thermal coefficient, its stiffness, its the D matrix, which relates to how it accepts electricity and electric fields. And then we're also given the polymer's dimensions, for which change based on thickness, which is what we had to optimize, and as well as its width and length. And then we're given some of its basic information as well. In this project, I mainly worked on the flex and the maple, not the final versions for the flex. I helped get the basis of the flex, and then the maple, which we used to test against, was mostly, which is like 99% my flex. My maple, I apologize. This is a diagram of the problem we were coming against. So our analysis and background theory. So we had to look at the stress and strain on a certain material related through Young's modulus, and from that get the temperature change with the thermal expansion coefficient, and the strain from the piezoelectricity, which we got from our D matrix, as I said before, against an applied electric field. Both these then had to be put into our curve equation, which took the moment of inertia of the piezoelectric polymer, and then as well as the electricity on it, and then the thermal on it. And then this curvature equation was then put into our tip displacement equation, which was half of the curvature output times length squared. To implement the flex, we based it off of the problem 4.2.2, the piezoelectric unimorph test, in which we changed variables and coefficients, of course, as well as some variable names. But the big things we changed was a lot of the thermal stuff in the question, as well as how it was modeled with the boundaries, as you can see in our comparison here. Next, we move on to validating. First, we briefly show here how we calculated our C matrix from the stiffness matrix using maple. Next, we show that we tested where it is getting strained, and it's all getting strained at the bottom, which makes sense since the bottom is fixed and it's bending on the other side. So this all validated that our flex was working properly. And then lastly, we also ran it through maple. So we put the equations in maple and then ran it through. As you see, the numbers are not perfectly exact, but close enough to say that our flex is working properly. Next, we move into our scripting. So the output the output from flex we put into our scripting was the tip displacement. And then we went into a grid search, which goes through and compares the values to each other to find a range of maximum values. We then went into a linear approximation, which got our line of best fit to show which direction it was going to for a gradient ascent. And then we put into a gradient descent, which slowly moved through and found our maximum optimized value. As you can see here, this is our after grid search, which you can see there was lots of noise, our linear approximation, and then our gradient ascent went into our conclusion, which we got to the conclusion that the best optimization, or the best optimization we found with our code, was 1,966 micrometers as the thickness and 2.896 micrometers of tip displacement. This is close to the range. We knew we wanted to be in the micrometers setting. The reason why we think this might not be the fully correct answer was there's lots of noise in the code, material properties, as well as numerical errors.